The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, good. So let me first remind you what we did last time. So last time we discussed that for any operator, say some operator O in the field theory, we expect there's one-to-one correspondence to some field, say phi, in the gravity side. Okay, and of course the quantum numbers of those they should match, because they fall into representations of some symmetry groups, and fall into representations of the same symmetry groups. Of course, their quantum numbers should also match. And in particular, on the field theory side, it's natural, say, to add a, say, if you have such an operator, it's natural to add a source term and then to deform the Lagrangian in such a form. And then we explained that then this phi may be considered as the boundary value of phi in the boundary of ADS. Okay? So the boundary value of phi, and it's mapped to the if phi have some boundary value, then that corresponding to your boundary theory Lagrangian have such a term in a Lagrangian. Okay? And then we also motivated this for, we also discussed this for the vector field and for the for conserved current. Say the case which is a conserved current, then that implies that in particular example of this, if you have a conserved current, then that's corresponding to you must be dual to a gauge field. And in particular, the stress tensor must be dual to the metric deformation in the field theory side. Okay? So any questions regarding this? Good. Okay. So now let's try to develop more the relation between this relation. So this is normally called the operator field mapping. And so now let's look at this relation a little bit more. So one immediate question one can ask, so there are obvious questions regarding, say, the spin of this operator, then should map to the spin of this operator, etc. But if you consider conformal theory, which is scale invariant, a very important quantum number for an operator, for scaling operator, is the scaling dimension. As we mentioned before, is that in the conformal theory, everything is scale invariant, and then you can assign any operator, any operator which transform on the appropriate representation of the conformal symmetry, a scaling dimension. That's one of the most important quantum number. So now let's look at how the scaling dimension of this operator are related to the physical properties here. Okay? Because here there's no low scaling dimension in the sense this is just some gravity field, and here is the isometry group. It's not the scaling symmetry. And then we also can try to understand what is the properties of this phi, how they reflected in O. Okay, so that's the purpose of today's lecture. So for this purpose, then now let's look at the gravity side. So as we said last time, we always work in the regime of the semi-classical gravity. So on the gravity side, okay. So what we will show is that actually the dimension of this operator can be directly related to the mass of the corresponding field in the gravity side. And so this is normally called the mass dimension relation. So now let's just consider on the gravity side, so the action can generically be written as the following. So everything is controlled by the gravitational interaction. So now I have introduced a new notation, which I will explain. So you have the Einstein gravity, and then you have some matter field, okay? You have some matter field, matter Lagrangian. So this is a generic form, say, of the action in the gravity side. So I've introduced this 2 kappa square, which is essentially the whatever is the Newton constant in this d plus 1 dimension. So the standard, normally we put the Newton 6 pi g, a Newton constant here. So g d plus 1 just means the Newton constant in g d plus 1 dimension. And I just now call this 2 kappa square for convenience, okay? And typically the matter field, say, suppose you have a scalar field, then you will have, say, following form. Plus, say, nonlinear terms. And if you have, say, the vector, say, if you have vector field, then you will have a Maxwell actions, etc. Okay, so just whatever matter field you have in the gravity side, and they just have this. So now let's consider small fluctuations. Now let's consider small perturbations around the pure ADS. Okay, so pure ADS, you only have a metric, and all the matter field essentially is 0. So now let's consider the small perturbations. Okay, around the ADS. Maybe I should say around the ADS. So first thing you notice is that this 2 kappa square is overall multiply the overall action. So that means that all the interaction here essentially are controlled by this gravitational interaction. Yeah, it's all controlled by kappa. Okay, and when you consider small perturbations, say when you then you can quantize these small perturbations, etc. It's convenient to use a canonically normalized action. So that means that, but if you look at the matter field here, the prefect there's 1 over 2 kappa square, which is a lot convenient. Okay, actually, then with that 2, then I don't need 2 here. So let me just get rid of the 2. So it's convenient to use a canonically normalized action. So it's convenient to consider small fluctuation around the ADS. Say, so convenient to canonically normalize. Yeah, 1 second. Normalize the kinetic term. Of small perturbations. Okay. So which means it's convenient when we consider, say, for example, the theory for phi. When consider scaling, say, take phi to, write, say, k phi equal to kappa phi prime, and then you consider the phi prime will have a canonical action. And say, for example, if you consider the metric perturbations, and then you can write it as h mn. So this is the ADS metric. Okay, then the phi prime and HMN will be canonically normalized. Okay. Yeah. So later I will just drop this prime. I will just call this phi. Okay. So we just do a scaling operation. Yes.
Why is it 1/2 should we get rid of?
Oh no, it's just because there has a 1/2 here.
But you have the R. You see the R is in the action and R should.
No, I'm talking about the matter. Matter field.
But in the action you write R minus 2 lambda plus the matter lambda.
Yeah.
So ordinarily it should be R plus 1/2 partial phi squared or something else.
No, it doesn't matter. It just how I normalize things.
Okay.
Yeah, you can normalize the. If you worry about 1/2, it doesn't matter.
Okay.
Here, we're not worry about 1/2. Yeah.
Okay.
Good. So now here's an important point. So here's an important point. Remember when we have the relation between the Newton constant, so the kappa square is of Newton constant. Remember, this is proportional to 1/n squared. Okay. Remember what we discussed last time. So that means under this scaling, so kappa is actually of order 1/n. Yeah, kappa is a Newton constant. It's a square root of Newton constant. It's very small. Okay, so this is in unit of literature. And we always consider in the Lagrangian limit so that the Newton constant is small. And so this is small. So in this regime, if we keep phi, so when we so for canonically normalized fields, say if those phi and HMN are of order 1, then their perturbation is naturally small. Okay? Then their perturbation is naturally small because they are essentially controlled by the scale controlled by the kappa. And that also means if you plug this into the action, so expand also nonlinear terms. Okay, so it also means that the nonlinear terms are order kappa or higher. Okay. Okay. So this is very easy to understand. So let's consider say a phi cube term come from here. So previously we have 1/kappa square phi cube term. Okay. So after this scaling, then I just have kappa phi cube. Okay. So for phi of order 1, then the cubic term will be suppressed compared to the quadratic term, because the quadratic term after the scaling will be of order 1. Okay? So the nonlinear term will be suppressed. Or higher and are suppressed. Okay. So except if we are interested in consider the contribution of those higher order terms, then to leading order we can actually just consider for small fluctuations, we can just consider the quadratic action. Okay. This means that to leading order, so we can consider quadratic action in ADS. So this means we can just, so this corresponding to quantize the free series. Okay. So this corresponding to quantized free series. So remember, we always use h bar equal to 1. So for those matter field, h bar is always equal to 1. And after you do the scaling, get rid of the kappa, and then we just treat them as the free field series quantization. Good. Any questions about this? Okay. So now let's look at a scalar field. Okay, just for illustration. Now let's look at what's the behavior of just a massive scalar field. So now let's consider a massive scalar field for illustration. And let's consider they have some scalar. We consider some scalar field phi in the bulk, which is due to some scalar operator O in the boundary. Okay, just imagine. Okay, so now let's consider the quadratic action for phi. Okay, so we can write down the quadratic action. So after you have scaled out this kappa, then the quadratic action can be written explicitly as the following. Plus all the kappa term. Okay? So this is just a free action. And the GMN is just the ADS. So the quadratic order, this is just in the pure in the background ADS. So we'll use this notation to denote the all component of ADS. Is the so we always use often use most of the time using this metric. Okay. This is my background ADS metric. And this is my action. So we'll also use the notation that the XM. Actually, I should write this a metric there, but it doesn't matter. So XM should be considered as Z, X mu, and X mu is the coordinates parallel to the boundary. Okay? So do you remember how to quantize the free field series action? So this is the time we need to remember that. So the first thing is that you solve equation of motion. Okay. So we don't need to go to details. I will just mention a few important features. Okay, so this is just the standard Laplace equation for massive scalar field, say in the curved space-time, and this GMN is just given by this metric. Okay. So this is a seemingly complicated partial differential equation, but here we have lots of symmetry. So there's a translation symmetry along the boundary, along the directions parallel to the boundary. Then we can just write down a Fourier transform. Okay. So because of the translation symmetries, in x mu directions. So we can just do a Fourier transform. We can write phi z x mu in terms of, say, ddk okay. So this k dot x is just the standard Minkowski contraction. Okay, because the t and x part, and essentially each slice is a Minkowski metric. So so my convention here, k dot x is just the standard Minkowski contraction. Okay. Standard Minkowski contraction. So now it's the Fourier transform. Then you have get rid of all the. Then you just plug this in. Then this is very easy to write down. And then the equation motion can be just the only derivative now would be just in the z direction. Okay, because then all the derivative in the t and x can be replaced by k. And then the equation becomes very simple. So take you a couple minutes to. Take you a couple of seconds to write it down. So so let me just write it down. So it can be written in the following form. Okay. And the k squared just is the standard one. Again, the k squared is just the standard Lorentz contraction. So omega would be the k0 in the time direction, with just the standard Lorentz contraction. Say k mu. Okay. So now this equation can actually be solved exactly. So normally when you quantize it, you solve the equation motion, then you find the complete basis of solutions. Then you expand in terms of that complete basis. Then the coefficient of the expansion would be your creation and annihilation operators. And then that's how you quantize the theory. Okay? So this equation can actually be solved exactly, so you can actually easily find out the complete set of modes. But it will be actually not needed for the current purpose right now. So, so let me not solve it, okay? So we'll leave it here. But what will be important for us is consider the asymptotic behavior of the phi near the boundary. Now let's consider the behavior of phi near the boundary. Okay, which will be very important for us is consider behavior. Yeah, now let's just consider behavior of phi near the boundary. So near the boundary, z goes to 0. So this term, compare this term is always much smaller because z goes to 0. M squared r squared is finite. Okay, so we can drop this term. But kinetic term typically cannot drop because kinetic term depend on well. So yeah, so we just throw away this term. So it's z equal to 0, and let me also write this, expand this term more explicitly. Then what do you find? Just drop this term and then writing this term more explicitly, then you find the equation can be written as following. Okay. So this is only valid when z equals to 0, leading order. Okay. So now this equation has a very nice form because this equation is homogeneous. Okay, because so z square, then the partial z square, z partial z, etc. And then you have this thing which there's no derivative, and so this is not some sense homogeneous in the derivative. Such kind of equation you can always solve it by some power of z. Okay, so let's just write down answers. Say assuming phi is proportional z to some power, and this power let me call it delta. So you plug this in, plug these answers into this equation, then you get the algebraic equation. So you can easily see from the first term you get delta minus 1. From the second equation, you get 1 minus d times delta, then m squared r squared equal to 0. Okay? And this is a simple quadratic equation. Now you can immediately solve. So you find two solutions. Okay, find two solutions. So we are writing this in the form 1/2 d plus minus nu. Okay, I will define this thing to be my nu. So this is the definition. Okay. So I will introduce the following notation. I will take the plus sign. I call the plus sign delta. So from now on, delta refers to plus sign. Okay. And then introduce sometimes I use a notation called delta minus, which is the minus sign, which is also equal to d minus delta. Okay. So this is the definition. So now I use this as a definition. So from now on, my delta is always d divided by 2 plus this number. So now what we have found, is that as z equal to 0, what we have found is that as z equal to 0, I have to let this stabilize. So z equals to 0, the phi kz have the following behavior. So you have two independent solutions. So then I can put arbitrary coefficient z d minus delta, two exponents, and another one is bk v to the delta. Okay? Then plus higher order corrections. Okay? So this is a leading behavior, two leading behavior in the z equal to 0 limit. And of course, I can also go to the coordinate space. Then this is just the xz, which is ax z d minus. Okay. So first notice that this exponent, this d minus delta exponent, is always smaller than delta. Okay? So this term always dominates. Okay? And so this is the leading behavior, and this is the sub-leading behavior. Okay? So keep this in mind. So now we have found the full asymptotic behavior of the solutions. Okay? And now we can discuss physics. Now we can discuss some physics. Now let me make remarks. So the first remark. Any questions so far? Good. So the first remark, you notice that this exponent are real if m squared r squared greater than d minus 4. Okay. Then you say, for sure, these exponents are all real, because normally we only consider the positive mass square. Okay. But actually in ADS, something very interesting happening. It's actually in ADS, the negative mass square also makes sense. In fact, you can show, as far as those exponents are real, means that as far as, so one can show as far as the star is satisfied, okay, the series is actually well defined. So in ADS, you allow to have a lective mass square. But if you violate this, then you find instability. Okay? This is a very nice story, but I don't have time to discuss in detail here. But I have my former student Nabil Akbar, when he was doing TA for me last time, he wrote a very nice note explaining how this works. And as I put that note on the web, so this equation is called the BF bound. The F is our colleague Friedman, and the B is a very complicated name. I always pronounce wrong. Yeah, so let me not try here. Anyway, so in the so Nabil gave a very nice explanation where this come from, and he shows that when you violate this, you actually get instability, and this maps into a very nice quantum mechanics problem, the quantum mechanics problem of -1/x². Some of you may have experience with that problem. Anyway, so please take a look at the notes I put it on the web, and it's a very instructive discussion. But we'll take a lecture to do that. Anyway, so now I just make the claim is that as far as those exponents are real, the series is well defined. Okay. But if this exponent is violated, then there exists modes which are exponentially growing in time, and then indicating the system is unstable. Okay. So this star is called the BF bound. Called the BF bound. Okay. So it actually is instructive to compare with a standard. Oh, actually, I forgot to use this blackboard. Okay. Anyway. Yeah, so instruct to compare with Minkowski spacetime. So let's compare with Minkowski case. So in the Minkowski case, if you have a free particle, say if you have a free massive scalar field, so of course we know this is our equation of motion, okay? And from here, because the Minkowski space every direction is translation invariant, then you just get this dispersion relation, okay? You just get this dispersion. Okay? You can write phi equal to minus I omega t. Yeah, let me just write it more carefully here. You can write phi equal to expansion of my omega t plus ikx. Then plug it in, then you find omega square equal to m square plus k square. Okay? So in Minkowski spacetime, we don't allow m squared to be smaller than 0, because if m squared is smaller than 0, okay, then that means for certain range of k, say for k, for those value of k which is smaller than the absolute value of m squared, then this will be negative. Okay? So for those things, the omega will be pure imaginary. Pure imaginary. Okay? You can be plus minus pure imaginary. And then you plug it in here, then you find the phi, then typically have exponential omega t plus exponential minus omega t. Okay? So the phi can have these two behavior. And then of course, this will exponentially grow. So this tells you that the magnitude of phi will exponentially grow with time. And so that indicates this instability. Okay? And so this is the same as the analog I said earlier before. In the Minkowski space-time, if you have a lactive mass square, and then your scalar field want to slide down, and this just tells you the behavior of its wants to increase. Okay. So this is the phi. So this is v phi. Then the phi wants to increase, and so this is phi equal to 0. But in ADS, something nicer happens. So in ADS, the instability only sets in if the mass square becomes sufficiently lactive. So if you just have the lactive mass square, if it's greater than this value, it's still okay. Okay? Still okay. So the reason is actually very simple. So the reason is very simple. You can try to convince yourself by looking at the equations, and you can see the physics from the equations. But the basic physical reason is the following. In ADS, okay, so you can just look at that equation. Because of the space-time curvature, okay, so the constant modes are not allowed. So you see here, the most dangerous modes are the constant modes. Okay, and when you have a constant mode, and then if m squared become, no matter how small it is, no matter how small m squared is, if you have constant mode, and then constant mode means k equal to 0, then that means that the omega square will always be negative. Okay, no matter how, as far as m squared is non-zero and negative, and there's always constant mode which is unstable. But in ADS, because of the space-time curvature, the constant mode not allowed. Okay. So you always have some kind of kinetic term in the sense that you always have some kind of kinetic energy. So a field is forced to have some kinetic energy. Okay, which can compensate this negative, which can compensate. This negative m squared. Okay, but this won't happen when the mass become too negative, and then you have instability. Okay, I suggest you. So this is just words, but those words can be reflected by looking at the structure of those equations and try to get some feeling about these words by looking at those equations a little bit more carefully. Okay, so this is the first remark. So the second remark is that we know that the ADS have a boundary. And the light ray reach the boundary in the finite time. So this is one important feature we discussed at the beginning. Reach the boundary in the finite time. In fact, in the ADS unit, it's just pi over 2 in the finite time. Okay, so that means actually energy can be exchanged. On the boundary. Okay, essentially you can send stuff in or send things out. Okay. And so we need to impose the. So in order to have a sensible physical system, you need to impose appropriate boundary conditions. Okay. You need to incorporate appropriate boundary conditions. So the most important basic criterion, again, we are not going into the detail. And again, Nabil's notes discuss this because he has to, in order to discuss instability, he has also to discuss the boundary condition, etc. And you can go to the look at Nabil's notes. So the basic criterion to impose a right boundary condition is to make sure that your energy is conserved, okay, and that your energy don't dissipate into nothing. Say don't dissipate at the boundary, and so that you have a well-defined system, okay. So that you have to have a well-defined system. Good. So now. So when you do canonical quantization, then what you do is that you expand phi in terms of a complete set of normalizable modes. Of course, they also have to be normalizable as normally in the quantum mechanics. Normalizable modes which satisfies the appropriate boundary condition. Okay. So before talking about the explicit boundary condition, let me first mention this issue of normalizability. So to talk about normalizability, you have to define an inner product. So here we just have we have the standard inner product for quantum field theory in the curved space-time. So here we have the standard inner product. Let me just write it down. So this is not specific to ADS. This is just works for any quantum field theory, for any free scalar field theory in the curved space-time. So you can define for that theory. You can define an inner product as follows. So consider you have two modes, phi1, phi2. And then the inner product can be defined as the following. You choose a constant time slice, okay? You have to choose a constant time slice, which I call sigma t. So this is a constant time slice. The time, I really mean this time, okay? You choose a constant time slice. And then of course, you integrate over spatial coordinates on this constant time slice. Okay? So this is the inner product. So this is a standard inner product. You can just plug in the ADS metric. You can just plug in the ADS metric that gives you the explicit form for the ADS. So if you're not familiar with this, and you can check that this makes sense, that by showing that actually this thing is actually independent of t. So it does not depend actually your time slice, okay? Because you don't want your definition of inner product depend on specific time you choose, okay? And then the normalizable would be the standard condition, whether this thing is finite or infinite, etc. Okay, and you plug in some modes with itself, and if it is finite, then it's normalizable, and if it's infinite, then it's not normalizable. Now you can, so now this is our asymptotic behavior, and you can check yourself. You can also convince yourself that the most dangerous behavior, because the metric diverges near the boundary. So the most dangerous part of this integral is near the boundary because because your metric diverges there. Okay, and you can just plug in this behavior and this metric behavior, and then just pay attention to the behavior near the boundary. Then you can decide which mode is normalizable, which mode is non-normalizable. Then you find, again, this takes you a few minutes to do, so I will not do it here. So I will also talk about only talk about the real U from now on. Okay, just real U. It means that we always satisfy that bound. Okay, so we find that for that mode, so this mode always goes to 0. Okay. So you have these two modes. This mode always goes to 0 because delta is always positive. Because nu is positive, and nu is non-negative, and d minus t over 2 is positive. So this is always goes to 0. And you can show that this is always normalizable. Okay, so there's no divergence at the horizon, at the boundary. But for this mode, you can see these modes become dangerous when the mass becomes very large. When the mass becomes very large, then the nu is big. Okay? When nu is big, eventually the delta can be pretty big, and then can be greater than d, and then this will be an active exponent, and then this will blow up. Okay? So it turns out this is actually non-normalizable indeed. So this is non-normalizable for nu to be greater than 1. Okay? You actually don't need to for mass to be very large. This is for nu to be greater or equal to 1, and this is already non-normalizable. But it's interesting thing is that this mode can also be is also normalizable when nu is in this range. Okay, in this range. Good. Any questions? Yes.
How can we define inner product some other way?
No, this is the only way. Yeah, this is a canonical way, just generic for quantum field theory in the closed space-time. This is not specific to ADS. For any, yeah, essentially this is a unique one. Yeah, I would say.
Yes. Okay, so I'm just trying to understand the inner product. So in the case that I take like make it a norm in the sense that I take the inner product of a field itself.
Right.
So why, for example, should this be positive? Like it's not.
No. This is in general not positive. Yeah, this is not in general. This is what we know in the Klein-Gordon field. Say if you do in the Minkowski space-time, this is in general not positive definite.
All right, that's right. Oh, I see. Sure.
Yeah. Same thing in the Klein-Gordon field.
Right.
Yeah, but you can. But nevertheless, so that means this thing does not make sense to interpret as a probability, but you can still use this as a definition of normalizability.
Right, but so it still has the property that something will only have a not, so it's not a semi-norm in the sense, like it is actually a good inner product.
Yeah.
Okay.
Isn't it just the generalization of the probability current in quantum mechanics?
Yeah. Yeah. No, this is the same as the Klein-Gordon equation. The same. This is the same inner product as you would define for the Klein-Gordon field, a free massive scalar field in Minkowski space-time, and this is just a generalization to a general curved space-time. Yeah. Good. So now, yeah. So we see that this is always normalizable, and this sometimes is normalizable, and sometimes not normalizable. So now let me talk about the boundary conditions. So for the time reason, I will not show that the boundary condition. So I will not show that the boundary condition I'm going to talk about will give you a well-defined energy in this sense that there's no energy exchange at the boundary. Okay, and for that, take a look at the Labiel's notes. I will not go into detail that, but the boundary condition I say will satisfy that property. Okay. So let's first look at when nu is greater than equal to 1. In this case, the answer is obvious. You don't even need to check the energy conservation, because you only have one possibility, because this mode is non-normalizable, and the non-normalizable mode you cannot keep them when you do the quantization. Quantization you have to use normalizable modes. So the boundary condition you have to choose in order to do canonical quantization is a equal to 0. Okay? So you should only keep this mode when nu greater equal to 1, because this is non-normalizable. So now, when nu is in this range, so both modes are normalizable, but you cannot choose both of them. You cannot allow both of them, because then it leads to the energy non-conservation. You need to put some boundary condition there. Okay. So then naturally the a equal to 0 will also work in this range. So this is called the standard quantization. Okay. You can still impose, even though the A modes become normalizable, but you can still impose A equal to 0. So alternatively, you can also impose B equal to 0. Okay, just take one of them, because because A now is normalizable, and so this is called the standard alternative quantization. Okay. So sometimes it's also possible to impose the mixed boundary condition between them. To impose mixed boundary condition between I will not go into there. Anyway, so you can easily check. For example, if you look at Labiel's notes, you can easily check for those boundary conditions that there's no energy flux through the boundary. Okay. So from now on, I will use the following terminology. From now on, we'll use the following terminology. So from now on, if I say normalizable, from now on, when I say normalizable, I always say the modes which are picked by the quantization. Okay. So when I say normalizable, in this case, of course, this is normalizable. Just, when I say normalizable, for nu greater than 1, there's no ambiguity, just the B modes. Okay? And when nu is between 0 and 1, the normalizable refers to the mode which you choose to quantize. Okay? And then the other you consider to be non-normalizable. Is it clear, the terminology? So in the standard quantization, the B mode is normalizable, and A is not normalizable, even though mathematically A is normalizable. And in the alternative quantization, the B is non-normalizable, even though mathematically it is normalizable. Okay, so by normalizable we mean boundary behavior. I mean the behavior specified by quantization. Okay, I call the other mode non-normalizable modes. So with this terminology, I always have one normalizable mode, one non-normalizable mode. Okay. Okay, let's move on a little bit more. So this is the second remark. And the third remark, let me just erase this. So the third remark, so normalizable mode by definition is the one we use to do canonical quantization, and it's the one we use to build up the Hilbert space. Okay. But now, since we have an equivalence between the two series, the Hilbert space of the two series should be the same, because otherwise the state of the two series should be the same. Otherwise, you cannot talk about the equivalence. So that means that any normalizable mode, so anything which fall off, say as the for example in the standard quantization, anything fall off like z to the power delta at infinity near the boundary, you should consider as mapped to some state of the boundary theory. Okay. So this is actually a very general statement. So this will also work if you include those higher order corrections which are suppressed by kappa. And they say, so in general, you can apply it to a complicated interacting nonlinear theory in the gravity side. And the normalizable modes are always the modes which in your Hilbert space in the gravity side. And so that means they must correspond to some states in the field theory, in the boundary field theory. Okay? Good. So now let's look at the interpretation of the non-normalizable modes. Okay. Non-normalizable modes, certainly they are not part of the Hilbert space. Okay. So if they are present, in particular, let me just finish this, then we'll say it. So if present, it should be considered. So sometimes they're just not present, okay? But if in some situation they're present, then you should view such kind of non-normalizable modes defining the background. So by background, for example, the ADS, pure ADS, which we are expanding around, is our background. And so you can imagine, say, turn on some non-normalizable mode to deform the ADS. Then you have a new background. And then that background you are not supposed to quantize itself because these are non-normalizable modes. Okay? These are non-normalizable modes. Yes?
Sorry, I guess I didn't quite get what the terminology normalizable is referred to, I guess. You mentioned it, but could you repeat it?
Sorry?
Normalizable, not normalizable.
Yeah. Normalizable means the behavior specified by the quantization.
But, so I don't quite get that. I don't quite understand, like,
Let me just repeat. For nu greater than 1, normalizable is just normalizable because there's only one normalizable mode. For nu 0 between 0 and 1, mathematically both modes become normalizable. But when we quantize them, we select one of them. Okay? As I said, in order to preserve the energy conservation, so we have to select one of them. So there are two possibilities. You select the standard quantization, which you set A equal to 0, or you set the alternative quantization, you set B equal to 0. So the one you set 0 is considered to be non-normalizable in this terminology. And the one you don't, the one you allowed, which means the one you are used to expand as a canonical quantization are called normalizable. Yeah. Yes. Sorry? I will elaborate this a little bit more. After 5 minutes, then you will see. Yes.
What do you mean by the other ones being present? If you don't quantize them, how do they appear?
Yeah, they can appear. I will again explain in 1 minute. Okay. So now I'm going to make a connection for this statement to the statement we are making last time. Okay. Same we are making last time. So last time we said if a gravity field have a boundary value, then this boundary value can be considered as a source multiply the operator, which you can add to a Lagrangian. Okay? You can add to the action. And so this is precisely like that. It's precisely like that. So let me just repeat. Yeah, say let's consider the standard quantization. Just to be specific, say standard quantization. Standard quantization. In this case, the non-normalizable mode corresponding to A not equal to 0. Okay, so if the non-normalizable modes are present, and this corresponding to the A not equal to 0. And we see from here, this term, A term, always dominates the other term. Okay? So in other words, when you go to the boundary limit, it's the A which determines the boundary value of the field. Okay? So A, standard quantity, let me just say, the A, which is determining the boundary value of the field. I quoted, I put a quote.
By standard quantization, you turn A to 0. Yeah.
A equal to 0 when you do the canonical quantization.
Oh, okay. Right. You turn it down.
By A equal to 0, you mean this is the condition on the normalizable mode. Oh, okay. So here we're discussing the interpretation of the non-normalizable mode. Okay. So now suppose A is non-zero. suppose the non-normalizable mode is non-zero. Okay? Suppose now the non-normalizable mode is non-zero. We are done with normalizable modes. This is a condition for the normalizable modes. Okay? So since this term dominates, the A should be interpreted as a boundary value of the field. And if you have a non-zero A, okay, so if you have a non-zero A, say if AX is equal to some phi x, according to what we discussed last time, okay, then up to this kinematic factor, which this thing which you need to strip away because because this just determines your equation motion. So if A equal to phi equal to 0, that should implies that the boundary serial action should contain a term OX. Okay? So what this means is that the non-normalizable, they are certainly not part of the Hilbert space. If they are present, they actually determines the boundary series, okay, the boundary series itself. So the non-normalizable modes determine the boundary series itself. So we will later see examples of this. But let me just repeat. Say if you look at the gravity, some gravity solution, then you look at its asymptotic behavior near the boundary. And if you see, say, let's say consider two different solutions. If the two different solutions have the same non-normalizable behavior, say the modes, non-normalizable modes are the same, but only the difference in the normalizable modes, then you will say these two solutions describe two states of the same series. Okay? Because they only differ by normalizable modes. Then they describe the different states in the same theory. But now if I look at two such solutions, and these two solutions differ by behavior of the non-normalizable modes, then we would say these two solutions corresponding to two different series. Because the non-normalizable modes leads to add additional terms to your boundary series action. Okay? Have I answered your questions?
So basically, you just assume any field which is like say linear combination of those two modes, but if the
now forget about linear combination of the modes. Just say if you consider two solutions, which if they are only differ by normalizable modes, then they corresponding to different states of the same series. And if they differ by non-normalizable modes, that means they describe different series. Okay. Even the series they describe are different. Okay? Is this clear? And so that's why we call this is background. Okay, we call this background because the asymptotic conditions at infinity has changed.
Okay.
But I have a question.
Yes.
So, but in the alternative standard quantization case that we choose b equal to 0.
Right.
But we know that the d minus delta is always larger than delta.
Right.
But in that case, it seems near the boundary, the dominant term is not the non.
Right. Yeah, that's a very good question. So that you have to stretch a little bit. Yeah. Good. So more precisely, so let me now finish my last equation before we break. So more precisely, because of this z term, okay? So in the standard quantization, yeah, let me just write it there. So write it here. So more precisely, in the standard quantization, let me just replace this one. In the standard quantization, that if you have a source, such a term in your boundary series Lagrangian, that's corresponding to this phi x is equal to limit z goes to 0, z to the power delta minus d phi zx. Okay? So I have multiplied a power so that it will just extract this a factor from the behavior of the phi. Okay? And so this is the relation. So this is the important relation. So last time we only said that the phi should correspond to the boundary value of this capital phi. But now, by working out the symptotic behavior, we have refined that statement. Now it's a really precise mathematical statement. Okay? Any questions regarding this?
Is it a guess or?
No, this is just a derivative. That procedure, this limit, precisely extracts this a term. This term, because that opposite power to this one, and this one will be smaller. This one will be smaller because this one, that multiply this one, when z goes to 0, will go to 0. So it will automatically extract this term. Exactly. Okay, it's the statement. It's just this statement that A is related to this. Okay.
Where did this statement come from? Is it just a guess or?
No, this statement is a guess from the example we discussed last time. So last time, by looking at this dilettante example, we deduce that the boundary value of a field should be related to the source. The boundary value of a Bach field should be related to the source of a boundary operator. And at that time, we don't know what we mean precisely by boundary value. And now we have worked out a precise asymptotic behavior, and now you can talk about what you mean by boundary behavior. And then that refines that statement into that precise mathematical statement. Good. So let's start. Okay, so now let's see what we can deduce from this relation. Okay, so turns out that there's a very important information you can deduce from this this equation. So this is my number 5. So let me call this equation star. So this equation star, relation star, actually tells you that this delta, which defined before in this way and appears in your asymptotic formula like this delta is actually the scaling dimension. Of the operator dual to phi of O. So we are assuming this phi is dual to some operator O in the boundary. And so this is actually precisely the scaling dimension of O. Okay? So now let me explain that. So now let me explain that. Okay, so before I do this, do you have any questions? Good. Okay, so let me first remind you how we define the scaling dimension of an operator in the conformal field theory. So if you have a scaling invariant theory, then the scaling, then the overall scaling is a symmetry. So such a scaling is a symmetry. Okay. And so under such a symmetry transformation, say operator, we call it a scaling operator if we transform under this symmetry as the following. So transform into a new operator prime and evaluate it at the new x prime is equal to just differ by a scaling from the previous operator. Okay, so we call the operator with such property a scaling operator. Okay, so operators which are good operators, which are say representations of the conformal symmetry, always have this behavior. And this delta defines the scaling dimension. So we'll scale the delta is the scaling dimension. So this is the definition of the scaling dimension. Okay. So this is almost similar to a scalar field. So scalar field means that the new scalar field evaluated at a new point should be the same as your old scalar field evaluated at the old point. And here the difference is just overall prefactor. And this number defines the scaling dimension. Good? So now I will derive that this relation implies that this operator transforms precisely according to this delta. Okay? According to this delta. So now let me first remind you that the boundary scaling x mu goes to x mu prime equal to lambda x mu is related to the bulk to also to isometry, which is x mu prime equal to lambda x mu. But at the same time, you also scale z. Okay. So this scaling symmetry, the counterpart of this scaling in the gravity side is that you scale both of them together. Okay. And the gravity matrix is invariant under this. It's invariant under this. Okay. So now let's consider such a transformation. So now let's consider the relation between the phi x z and the ox. Okay. So let's consider such a transformation on both sides. So on the gravity side, such a transformation leads to a new field. And this should be dual to a transformed field on the field theory side. Okay? Okay. Sorry? Which flip?
Left, right, vector, fine. Oh, boundary. Boundary is to the left.
Oh. Yeah, that's right. Yeah. That's right. Now this is spark. This is the boundary. Okay? But since this is a symmetry, so this transformation of both symmetries in the field theory side and in the gravity side, that should have low consequences. Okay, that should have low consequences. That means okay, and the phi prime, this small phi is the boundary value of the corresponding capital phi. Okay. This should still be the same, because your physics should not be changed under this. Okay. So now let me remind you that phi is a scalar field. In the gravity side, this is a scalar field. So scalar field transform under such a coordinate transformation transforms as phi prime, x prime, z prime equal to phi xz. Okay. Okay, so this is just the definition of the scalar field in the gravity side. And now let's apply this to the boundary value. Then we find that phi prime x, which is the boundary value of capital Phi prime, okay? So this should be equal to that. So now we use this relation that z prime is lambda times z. And this is just equal to that. So this just become lambda to the delta minus t phi x. Okay? Clear? So now you can just plug this back into here. And this, so there's a factor of lambda minus delta minus d. And this comes with a factor of lambda to the power d. And then tells you that O prime x prime equal to lambda minus delta O x. Okay? And we show that this delta, which appears here, or whatever here, is that delta, is the dimension of the operator.
Oh, but in standard quantization, you mentioned that
No, this is a standard quantization.
yeah, A equals to 0.
Hmm?
In standard quantization.
No. We are talking about the source. We're talking about non-normalizable modes. We're not talking about canonical quantization. No, we're not talking about canonical quantization. We're talking about the attending on non-normalizable modes corresponding adding such a source, adding on such a term to your action.
But isn't that a field operator correspondence?
Sorry?
Isn't that a field operator correspondence?
Yeah, this is.
But these are non-normalizable.
Yeah.
Field operator correspondence.
Yeah, that's what we. Yeah. So we are talking about the non-normalizable modes, and the non-normalizable modes corresponding to turn on an operator, turn on a source to operate in the boundary theory. And just this relation, and it shows that the delta is its dimension. Any other questions?
So then when we quantize everything, this operator O is dual to normalizable capital Phi or non-normalizable?
No, here we are talking about the question. Here we are talking about this relation. That if there's a boundary value of capital Phi with this boundary value, then that's corresponding to add such a term to your Lagrangian. And under such a correspondence, then we deduce that this delta is the dimension of this operator. Is the dimension of this operator. And this is deduced from the non-normalizable perspective. And then indeed you can ask, say, suppose I create modes, create normalizable modes using this phi, using this O, whether that is consistent with that. Indeed, that you can double check. Is it clear? Yeah, anyway, so this is what we have right now. So later we will discuss the correspondence for the normalizable modes. And we worry about later. Yeah, later we will talk about the correspondence for the normalizable modes, and then you will see it's compatible with this relation. Okay, so now we find for scalar, okay, for standard quantization, for scalar, in the standard quantization, for scalar in the standard quantization, that the dimension of the operator related to the mass in the gravity side by the following relation. Related to the gravity side by this relation. Okay. So we have found the explicit relation between the conformal dimension and the mass. So now, let me elaborate a little bit on this relation. So let's consider, suppose the m equal to 0. Okay, when m equal to 0, then you have just, then you find the delta equal to d. So delta equal to d on the on the field theory side, this is a marginal operator. Okay, this is a marginal operator. And so we see that the massless field on the gravity side is mapped to a marginal operator. Okay, it's mapped to a marginal operator. So are you familiar with the terminology of the marginal operator, relevant operator, etc.? Good. And
wait, can you remind us what is it?
Yeah, this is defined in terms of the RG flow. Are you taking the quantum field theory too?
Yes. We haven't quite got. Okay, fair enough.
Yeah, then you will be then you will get there maybe in a week.
Okay, great.
In a week or two.
Yeah, certainly by the end of this semester. And you should, yeah.
Okay, great. Okay.
Yeah. So so let me just say one. Yeah, I will say a few more words, and then you will see what it means. Okay. Yeah. Yeah. Just I will say a few more words. Anyway, so when m squared is smaller than 0, then here is negative. Okay. Then this d squared over 4 matters something. So that means the delta is smaller than d. Okay, when the dimension of the operator is smaller than the space-time dimension, so that from field theory called nu is called the relevant operator. Called the relevant operator. And now, when m squared greater than 0, the map to delta greater than d. So this is a map to an irrelevant operator. Okay.
Why they have this name?
Why they have this name? Marginal, relevant, or irrelevant? Yeah, I will say a little bit about that. Okay. Yeah, just wait 1 second. So now let's see what this means. Now let's see what this means from the perspective of this relation. Okay. So from the field theory side, yeah. So let me write it here. So from field theory side, we have phi x, Ox mapped into. So this phi should be identified with A. So this is identified with this term, d minus delta. Okay, leading term. Okay. Okay, so now let me remind you what this marginal and relevant irrelevant means. So when marginal, when we call an operator marginal, means when you add such a term to your Lagrangian, the effect of such a term does not change with the scale. So whether you are looking at very high energy, looking at very low energy, the effect does not change very much. Okay, so that's why I call marginal operator. So there's a very, in the realization group, there's a very simple scaling argument to show that when the delta is equal to d, and then the effect of the operator does not change. It does not change with the scale. Yeah. In particular, when you go to the UV, this does not change. Okay, for marginal operator. Okay, when you go to UV, say when you go to higher energy, the effect of this operator remains the same, roughly. So now we know from this IR-UV connection, UV mapped on the gravity side to z goes to 0 means we are approaching the boundary. And now we see precisely for d equal to delta, this term is actually constant. So go to smaller and smaller z, and the effect of this term does not change. It's just a constant. So again, does not change. Okay. So now let's look at the relevant operator. So the relevant operator. So in the field theory, when you do the RG, the relevant and the irrelevant means whether this term become relevant when you go to the IR. Okay. By relevant means that the term become more and more important when you go to the low energies. Okay. So that means that for the relevant operator, when you go to high energies, it becomes less and less important. Okay? By definition, the relevant operator means when you go to low energies, become more and more important. And it means when you go to high energies, become less and less important. So it means that when you go to UV, the relevant operator becomes less and less important. So now let's look at this side. The relevant operator corresponding to delta smaller than d, then you have a positive power. Positive power. Then that means when you go to z goes to 0, when you go to UV, actually this term goes to 0. So this is precisely compatible with the field theory behavior we expect when you add such a term to a Lagrangian, and the effect of such term should be less and less important when you go to the high energies. And here we see a precise counterpart here. Okay. And similarly, now if you go to the irrelevant operator, irrelevant means irrelevant when you go to IR. When you go to UV means more and more important. So that means, but here when delta is greater than d, then here have elective power. So here it goes to infinity, become bigger and bigger, and indeed this term become more and more important. So we see a very nice correspondence between this behavior we expect just from the ordinary RG and the behavior of this term in the gravity side. So this is a very important self-consistency check of our matching, both of this relation, and of this relation. Okay. Any questions on this? Yes?
What's the topology of ADS boundary?
Sorry?
What's the topology of ADS boundary?
It's a Minkowski space.
It's not S5? It's not like S5 times something?
No. The ADS is just Minkowski space. Yeah, boundary of ADS is just Minkowski space.
I have a question. Maybe just like, can you remind me, like, in RG, why this means it doesn't change?
Oh, no, that takes some story to do. Oh. Yeah. Yeah, that you have to do in the quantum field theory too. Yeah. Yeah, but if you just yeah, but it's very easy to understand. It's very easy to understand if you just know a little bit free field theory. If you just know a little bit free field theory, and when you in the field theory point of view, when the dimension of this operator is smaller than the dimension of the operator, and then this is dimensional, then this have a positive mass dimension, And then this is like a mass term. And the mass term become more and more important when you go to low energies.
Oh, I see.
And become less and less important when you go to high energies. Yeah, just from dimensional analysis.
Okay.
Yeah, it takes maybe 5 minutes to explain very clearly, but we don't have these 5 minutes. Okay, so let me just summarize. We have this relation. Yeah, let me just summarize here. So we have those relation. So summary. So we have phi dual to some O. So here normalizable modes should be considered different normalizable modes corresponding to different states. And here non-normalizable modes is mapped to different actions. So if you have different non-normalizable modes, then you map to different actions. You map to different series. So in other words, map to different series. Okay, map to series. So when you turn on the non-normalizable modes, you are deforming the theory. Okay. So just to elaborate, just more precisely, in the standard quantization, which is A modes are non-normalizable. Okay. When the A modes are unnormalizable, then AX on the gravity side is mapped to this source term on the gravity on the field theory side. Okay, if you have a non-zero AX, the map to the following term in your action, and then your mass we deduce that on this side is mapped to the dimension, the delta, given the delta dimension of this operator O. So later we will explain as part of this normalizable mode story. So this B, so A is non-normalizable, but B is normalizable. So later, as we will explain in the normalizable mode story, is that the Bx here will actually map to the expectation value of the O. Okay, so B is a normalizable mode, then actually that maps to the normalization expectation value of O in the corresponding states. Okay, in the corresponding states. And so A map to how you deform the theory, and the B just map to the state which specify your expectation value. So this we'll see later. And in the alternative quantization, you just do it oppositely. In alternative quantization, you just switch A and B. In alternative, you just switch A and B. So now B map to EXO, and AX map to the expectation value, and M now map to D minus delta. So now the dimension of the operator is D minus delta rather than delta. So now because you just take the different exponents, okay, it's the same thing. Just take different exponent. So now the dimension of the operator is D minus delta. So now let me also mention some other examples. So you can also consider gauge field. You can consider, say, a Maxwell field in the gravity side. Then that will dual to some conserved current, so we said earlier. And then you can check. Then again, you just solve the Maxwell equation, which I will not have time to do it here. but I may ask you to do it in your P set, is that A mu as equal to infinity become, so the boundary, so the part of A parallel to the boundary goes to a constant. There's no z, just really a constant, plus B mu some number to the z to the d minus 2, d minus 2. So this is a leading behavior in the case of the vector field. Okay. So using the very similar scaling argument I was doing there, you can deduce that the operator dual to A must have dimension d minus 1. Okay, this I will leave to you as an exercise. Just exactly parallel a statement as we did for the scalar case. And with this asymptotic behavior, you can show, just using the argument, you can show that the operator dual to A must have dimension d minus 1. And this is precisely the dimension a conserved current must have. So a conserved current, because it's conserved, so its dimension actually is it's actually protected. So no matter in what kind of interaction, no matter in what kind of case, always have the same dimension d minus 1. And so this precisely agrees with that. So do you understand why?
The why?
The reason is simple. It's just because it's just because J0, the dimension of the J0, you can understand as the following. The J0 is the charge density. And the charge density by definition does not have a dimension. And by definition, the density always have a dimension minus 1, d minus 1. And then the other component just followed by the conservation. Okay, and the other component followed by the conservation. Yeah, so indeed, this is a consistency check.
So for this case, there is no choice of quantization. It's only one.
Yeah, there's no choice for quantization, right? Actually, in ADS4, in some special dimension, you can also do a different quantization. But the story is a little bit subtle. Yeah. In some special dimension, sometimes you can do it. Yeah, in ADS4, you can do a different boundary condition. So now let me also mention the stress tensor, which is the other important one. So we mentioned that the stress tensor, which is dual to the perturbation of the metric component. Say if you write the ADS metric as some function times dz square plus g mu mu dx mu. So this is the part of the metric parallel to the boundary. Then we discussed last time if g mu goes to the boundary as something like this, that eta mu plus some perturbation, then that means that in the field theory side, you are turning on a stress tensor perturbation. Okay, so that's what we argued last time. If the boundary value of your Bach metric, say, is perturbed away from the Minkowski metric, then corresponding from the field theory point of view, you turn on a source for the stress tensor. So again, by using this relation, you can deduce that the stress tensor must have dimension, the corresponding operator must have dimension d. Again, this gives you exercise to yourself. And again, that is precisely the stress tensor, the dimension should satisfy by stress tensor. And again, because the stress tensor is a conserved current, etc., and always, no matter in what kind of theory, always have dimension d. Okay? Oh, so now after I've discussed this relation, let's now discuss how to compute the correlation functions. Okay? So let's discuss how to compute correlation functions. So the basic observable in the field theory, even more so in the conformal field theory, is just correlation functions of local operators. They are an important part of the. And in the field theory, typically when we consider the correlation function of local operators, we use something called the generating functional. I hope you're familiar with. Say, again, generating functional is, so now let's consider Euclidean, which is a little bit simpler. So essentially, it's a Euclidean correlation function by adding such a term to your field theory. Okay? And if you want to calculate correlation functions of O, then you just take derivative with phi, and then set phi equal to 0, then you get the correlation function of O. So I hope you're familiar with this, okay? So here, you should think of O, phi, and O as just some really a collection of all possible operators. Even though I just write the single one, you should think of them as a collection of all operators. You can put anything here. Stress tensor, conserved current, any scalar operator, any spin operator. Yeah, you can put anything there, okay? So in a simplest situation, you just don't turn on any operator. You just write phi, just take phi equal to 0. So this is simplest situation. Then you just have the partition function. So this correlation function is defined by the Euclidean path integral, for example. And you just insert this in the Euclidean path integral. And when phi equal to 0, this is just the Euclidean path integral. And this is just giving you a partition function of the whole system. And since we believe the duality should be true, then this partition function should be exactly the same as the partition function on the gravity side. Okay? Suppose you can compute the partition function on the gravity side, then they must be the same. Otherwise, there's no equivalence. So this is the partition function of the gravity side. Gravity field. Okay? So this have to be true. So now with this relation, again, I will write in the heuristic form that some operator O is dual to some Bach field phi, and the source for the O is dual to the boundary value of phi. Again, I write in the heuristic form. So the boundary value of phi should be understood in that limit. Because of this, then that means we must have now if we turn on a non-zero phi, deform the theory by this phi, then must corresponding to the gravity side, the partition function. Now with this phi, have the boundary value given by phi. Then it must be the same. Okay? Because we have identified turning on the boundary value to turning on the operator, turning on this thing in the field theory. So we have now relate the generating functional to the gravity partition function with some non-normalizable boundary conditions. Okay, with some non-normalizable boundary conditions. So in general, yeah. So now let me give me one more minute. So in general, this equation is actually empty because we don't know how to define the gravity side. Okay. Yeah. How full quantum gravity partition function? What are you talking about? We don't know how to do that. But we know how to compute this guy in the semi-classical limit. which is the string coupling goes to 0 and alpha prime goes to 0 limits. Okay? So in this limit, we can just write the gravity path integral, gravity partition function, essentially as a Euclidean path integral over all gravity fields. Again, I'm using this heuristic form to write the boundary condition, but it should be understood in that form. And again, I'm by integrating over phi, you should imagine integrating over all gravity fields. Okay. So now in the limit, so this SE is proportional to 1 over kappa squared, which is the Newton constant. So in the semi-classical limit, in this limit, the kappa squared goes to 0. So you can actually evaluate this path integral using the saddle point approximation. Okay? In the saddle point approximation. So at the leading order, so this gravity can actually be evaluated. So leading order in this semi-classical limit, you can just evaluate it by saddle point approximation. Then this is just given by SE, evaluated as the classical solution. Okay? Classical solution. Classical solution, which satisfies the appropriate boundary conditions. So that means actually, in this limit, we can actually evaluate this explicitly. And the nice thing is that we said before, this semi-classical limit actually corresponding to the strongly coupled limit in the field theory. So we can actually compute explicitly the generating functional in the strongly coupled limit of the field theory. Okay? Yeah. So let's stop here.